All right. Well, I hope you guys are having a great day. Today, we're going to be talking about how to use partial fractions decomposition in order to integrate a rational function. Now, you might recall we used this technique earlier when we were integrating rational functions in which the denominator had roots which were distinct. Today, we're going to be looking at how to integrate whenever the rational function has a denominator, whenever there's going to be a repeated factor. Now, the first thing that I want to do is take our rational function and do a little bit of decomposition. So I do have my denominator, which has already been factored. I'll have our 2x plus 1, and we'll have our x minus 2 quantity squared. So whenever I do my decomposition, I'm going to have a value of a over a 2x plus 1. I'm also going to have a value of b over x minus 2. But due to the fact that I do have a squared right here, I have to account for that repetition. Therefore, what I'm going to get here in the end is I'm going to get a value of c over x minus 2 quantity squared. Now, from here, the next thing I want to do is take our rational equation and turn it into a polynomial. I do that by multiplying both sides by my denominator, the 2x plus 1, x minus 2 quantity squared. When I do that, this whole entire rational expression, or this equation, is going to give me a value of x squared minus 5x plus 16, which is going to equal a value of a, and then I'm going to have a 2. I'm going to have my a, and I'm going to have a value of x minus 2 quantity squared. Then I'm going to pick up a b, I'm going to have a 2x plus 1, and then an x minus 2. Then I'm going to have a c, and then a 2x plus 1. From here, what I want to do is start picking choice values for x, such as what if I was going to set x equal to 2? If I do that, then on the left-hand side, I'll pick a value of 10, wherever I take this and I plug it into my polynomial. On the right-hand side, though, the first component is going to zero out because x minus 2 is going to correspond to 0. Also, the b term is also going to zero out over here as well. Therefore, I am going to get my value of 0 plus 0, and then at the very end, I will get a value of 5c. Therefore, upon simplification, I see that c is going to be a value of 2. Now, the next thing that I want to do here is pick something else, such as what if I was going to choose x equal to negative a half? If x equals negative a half, whenever I plug into the left-hand side, what I'm going to get is a value of 75 over 4. On the right-hand side, what I'm going to get is a, and I'll have negative 5 over 2, to which I'm going to square. Now, the other components over here are going to get you a value of 0. Therefore, upon simplification, what we find out very quickly is we're going to get a value. We're going to have 75 over 4, and we're going to have 25 over 4a. Multiply both sides by 4 over 25 and 4 over 25. Doing so is going to reveal that a is going to have to be a value of 3 in the very end. So far, we got our values for a and our values for c. Now, we're kind of in a conundrum. What are we going to do next? We're going to use the values for 2 and use the values for negative a half. We have no more roots to choose from. In this particular instance, what we can do is we can choose whatever we want for x. We can let x be a value of 0. Now, if x is a value of 0, when I take this and plug it into my equation, I see that I get a value of 16 on the left-hand side. Whereas on the other side, we get a value of 4a and then minus 2b. And then I'm going to get a value of plus c. Now, recall that we actually know what a is. A is going to be a value of 3. We can plug it in. C is a value of 2. We can plug that in as well. Whenever we do this, we find out that we're going to have is 16, and we're going to have 12, and then minus 2b, and then plus 2. Whenever we simplify down here, we find out that b is going to have to be a value of negative 1. Now, with these values in hand, we can come up here and we can update our equation. We know that a is going to be 3, and we know that b is going to be negative 1, and we know that c is going to be 2. Using this, we can take our polynomial, or our rational equation, which was going to be our x squared minus 5x plus 16, all over 2x plus 1, x minus 2 quantity squared, and we can take this and rewrite it. We'll have our 3 over 2x plus 1, and we'll have our b all over our x minus 2. And then we'll have our minus, our c, x minus 2 quantity squared. Now, once again, the values for our b, that's going to be our value of -1. And our value for c, that's going to be a value of 2. So we can simply take those and plug it in. From here, the next thing is we'll go ahead and integrate both sides. If I integrate the left-hand side, I would integrate also the right-hand side. When I integrate the right-hand side, I see that my first integral right here, that's going to correspond to 3 over 2, the natural log of the absolute value of 2x plus 1. Whereas the next integral is going to get me a value of negative, the natural log of x minus 2. And then for the last one, what we're going to find out is we're going to get our -2 over our x minus 2, and then plus c at the very end. So partial fractions decomposition, it's a very, very powerful technique. It's very useful to help us to integrate rational functions, which other methods are just going to leave us a little bit of a loss.